let's continue the discussion. Okay. So we already talked about how we can, do the diagonalization in like for complex matrices, but it's not necessary. Okay. The case for all the complex matrices, because it's not necessary all the complex matrices have like distinct n diagonal orthogonal vectors, right? Eigenvectors, right? Because you see, like in order to have this, okay, we have to have distinct, eigenvalues. I mean, here, okay. It's column vectors from an orthogonal set. So, I mean, it's not necessary all the complex matrices are unitary, right? So this is not necessarily the case. So how about for general matrices? Okay, we have this. For each n by n matrices A, okay, so this is not, so for not, I mean, we don't have any prerequisite for this matrix A. 就是 A 没有任何的，这个发回给大家是不是 ？OK， 就说 A 没有任何的那个要求哦，任何的 matrix A。There exists a unitary matrix U such that UHAU is upper triangular. Okay, so even though like we may not be able to diagonalize any n by n matrix, okay, at least we can make we can do this this thing to make like this decomposition upper triangle, okay, which is pretty good already, okay. So we call this factorization A equal to UT. This T is represent that upper triangular matrix, okay. UTUH is referred to as sure decomposition of A, okay, because T equal to UHAU. So from here, I mean, of course, we can get A equal to UTUH, right? Remember, UH is U, the inverse of U, right? So this is like so once we have the theorem, okay, the following is like is obviously the case. So it's so we say A equal to this one is the sure decomposition of A. If A is Hermitian, the matrix T will be diagonal. So A, the requirement for A to be diagonal is A is Hermitian. Okay, so we need to prove this. Okay, so this proof is by induction. Okay， 等一下我看一下，我这样子还剩下几页啊？今天来几来不及？大概这个 section 吧。Yeah, I think we probably can just finish this section and that's it for this semester. Okay, so this theorem, okay, if you want to prove this by induction, okay, this is obviously true when n is 1, okay, I mean, when n is 1, like, the size is 1, it's 1 by 1, so it's basically just one number, okay, so the UHAU, okay, upper triangle, because, if you have only one number, no matter what you do to it, okay, one number is already upper triangle, right? There's no way you can 就一个数字它就已经是上三角形的矩阵了嘛，对不对？对不对？你知道我意思？就是你要不是上三角形矩阵，你的矩阵至少2乘2嘛，对不对？对不对？所以 so basically n is 1. I mean this result is obviously true. I mean, but assume the hypothesis. I mean then we assume like because it's a induction, so we assume like this properties hold. I mean hold for n by k by k matrices. Okay, then we want to show that this can be the same thing can be said for k plus k times k plus k matrices. Okay, so if we have a k plus k by k plus k matrix, okay, then that lambda 1 to be the eigenvalue of A, that W1 to be the unit eigenvector, okay, of the corresponding, corresponding to like a lambda 1. Okay, then we know like the Gram-Schmidt process can be applied to the complex complex matrices as well, right? Do you guys remember Gram-Schmidt? Gram-Schmidt is like it's a process that allowed us to build orthogonal orthonormal basis out of any basis, and if you Gram-Schmidt is not this chapter, I believe. It's I believe it's sorry. Yeah, this one. The important thing is that, okay, for any matrix, okay, we can compute the Gram-Schmidt like a decomposition, such that like okay, here, okay, the second part is an upper triangle. Okay, so if you forget about this already, please refer to the previous chapter. We have a section dedicated to this thing, but obviously we are running out of time, so let's okay. So basically, okay, we can use this process to construct orthonormal bases from any base, okay, any base. So W1, W2, blah, blah, WK plus 1. So this W1 is the, we just pick W1 to be the eigenvector corresponding to lambda 1, okay, and then our WHAW is going to look like this. Okay. And then, okay, okay. We know like M is already K by K, so we can, there exists a K by K unitary matrix V1, okay, such that V1H M V1 equal to T1. So we can upper triangular, create upper triangular T1, okay, by applying like the unitary matrix V1, okay, to M, okay. So because T1 is triangle, okay, then we can let V to be this one, okay, and then okay, because V is a unitary, okay, and then VHW HAWV, okay, we, the inside here, okay, let me see, V1WH. WHAW is this one, right? So WHAW, okay, is this one, and the inside here, because we use a VHV, okay, so we have this one. Okay, we apply the V1, HV1 in here, okay, because when you apply V on the on this one, okay, the result is going to be the V1 HM V1 is going to appear here. The other parts remains like that. Okay, this is just a matrix arithmetics. Okay, in a matrix在矩阵里面，我们常常在做，有一些时候我们常在做那个，譬如说，你矩阵可以把它切开来，譬如切开来 A B C D 乘上 D 啊，不是 E F G H。那这个每一个都是一个矩阵哦，都是一个大的矩阵。然后，但是只要它们的 size 是一样的，它可以变成这个，就变成就好像说你这2乘2的矩阵，这边变成这一块，就变成AB plus 对不起 AE 啊 AE plus 那个 BG 啊点这个就是这个是 this is like just a matrix like manipulations only like which we really didn't talk about this very much, but hopefully like this is something obviously to you. Okay, so same thing applied. Okay, you just this one. Okay, if you multiply it with this thing, okay, on the at the beginning, I mean in front at the back, so only this part will be affected. The other parts remains like that. Okay, because like the upper left is going to be lambda 1, I mean times 1, so it remains to be lambda 1. This part remains to be the same thing. Okay, this part is 0. Okay, because these are all 0. This part, I mean, they may have something, okay, but that's fine, okay, it doesn't matter. The important thing is this one. It's V1 HM V1. So remember, V1 HM V1 is already upper triangle. So this one we may have something, but this one we already have upper triangle. So it shows that the whole thing is an upper triangle matrix, okay? And the last thing we need to show is that WV is a unitary matrix, okay? But this is also very simple, okay? Because matrix U, we know matrix U is unitary because, okay, the UH times U will be, this WVH times WV. I mean, it will be VH, WH, WV. And we know WH times W is I, and VH times V is I, so the result is I. So we know, WV is a unitary matrix. Okay? And so we have this. Okay, according to the induction. So, and another thing we haven't proved is this one, right? This factorization, okay, here, if A is a Hermitian, the matrix T will be diagonal. We haven't proved this part, okay? I mean, the proof previously, I mean, the induction proof previously, we just show the theorem. We just show the theorem, okay? But this sentence, we haven't proved it yet. So this sentence is actually called spectral theorem, okay? If A is Hermitian, then there exists a unitary matrix U that diagonalizes A, okay? So the proof is actually very, very simple, okay? So there is a unitary matrix U such that T equal to UHAU. We already know that from the Schur theorem, right? From the Schur theorem, where T is upper triangular, okay? And if you try to do TH, okay, TH, I mean, obviously is this one, right? So it's going to be UHAHU, right? But the AH is already A, right? So it means this one is this one, which is T, right? So if TH equal to T, what does it tell us? If TH equal to T, the only thing that this is possible is that this T is diagonal, right? It's diagonal. I mean, it's Hermitian, obviously, but also, I mean, it's Hermitian because it's according to the definition. If TH equal to T is Hermitian. But if a square matrix is Hermitian, then it must be diagonal, right? It must be diagonal. Okay, and also we know like the diagonal elements will be real, right? As I already told you previously. Okay, and these also have a very interesting corollary. If A is real symmetric matrix, okay. If A is real symmetric matrix, remember, if A is real symmetric, that means what? That means A is Hermitian, right? So if A is Hermitian, okay, then there exists an orthogonal matrix U that diagonalizes A. This is obviously the case, right? This orthogonal matrix is exactly the U, right? Right? I mean, we can get it from the spectral theorem directly. So the example, I think like, yeah, I mean, this one takes some time, but this is obviously symmetric, real symmetric matrix, right? So you can compute like its eigenvalue and the corresponding eigenvector. So here, okay, you can see like the eigenvalues are -1 and 5. So when eigenvalue is -1, we have two vectors, 1, 0, 1, -2, 1, 0. Okay, and eigenvalue is 5, we get this eigenvector. So for these three eigenvector, you can apply Gram-Schmidt process, okay, to get like your W1, W2, and W3, okay. I mean, so that you have these three. From the W1, you get this one. From W2, okay, you get like actually here, even though if you remember, I mean, we talk about Gram-Schmidt process. It's you need to subtract the projection part. Remember, you need to get rid of projection part. Okay, to get only the orthogonal part, remaining orthogonal part. But here, it's simple. Okay, why? Because, okay, the different eigenvectors, I mean, must be diagonal, must be orthogonal. Okay, different eigenvectors must be orthogonal. So the only thing you need to do is really like, make sure like they are. I mean, these vectors are like a unit. I mean, in length. So you need to divide like the length. Divide the length. Okay, divide the length. Okay. So I mean, these are the three column vectors. These three column vectors are from your eigenvectors. And UHAU is going to be this one, where the diagonal elements are the corresponding eigenvalues. I mean, of course, like here I just hand wave this part. You should do a little bit of computation by yourself to verify this. Okay? 可以吗？这边 ？Okay, good. 有问题吗 ？OK， 好，最后一个，都来急还不急 ？Normal matrices, OK. Some non-Hermitian matrices possess complete orthonormal set of eigenvectors. 这边就有一些不是 Hermitian matrices， 它还是有可能有这个 orthonormal set of eigenvectors. OK， 那这边给那个例子是这个 skew matrices 跟这个 skew Hermitian matrices。什么叫 skew symmetric 跟 skew Hermitian matrices？OK， 先讲 skew Hermitian matrices 好了。skew Hermitian 就是说 AH 等于负 A。OK，we say a matrix is Hermitian if AH equal to A, right? So skew Hermitian just means we add a negative term there. So the skew symmetric means like, okay, this is applied to real matrix, okay? For real matrix, okay, if your AT equal to negative A, okay, the transpose, your transpose equal to negative, your negation of yourself, okay? So 对这个你可以想象哦，在这种 skew symmetric 或 skew Hermitian 哦，它的这个对角线的那个 the diagonal elements must be 0. Okay, must be 0. If it's non-zero, it's impossible, right? 对不对？这边顺便讲一下，这个你们可以自己去看一下。OK， 好 ，Anyway。If A is a matrix with a complete orthonormal set of eigenvector, A equal to U D U H， 就我们这边下面要秀说这个东西有可能啊。OK，where U is a unitary and D is a diagonal。前面有点像是说我们如果说 A is a Hermitian， 我们知道说这个它有一些很好的性质。那我们现在反过来说。如果说有这些性质，反过来它是怎么样？原来的矩阵是怎么样？好，所以 OK， 所以 A 等于 UD UH。Okay, U is unitary, D is diagonal matrix. So in general, DH and D are not the same in general. Okay, I mean at least it's not something that we can assume. Okay, and AAH equal to AHA. Why? You can verify this. AAH equal to UDUH, right? Times UDHUH. I mean, well, you just apply like H on A, you get this. And the UHU is because it's a unitary, right? So this one is I, right? This one is I. So you get a UDDHUH, right? But the other way around, AHA, you get this, right? So same thing, the middle part cancel out each other. So you get this one, right? Okay, so, but remember, D is diagonal already, right? I mean, for diagonal matrix, I mean, DDH and DHD are the same, right? Okay, so that's why AAH and AHA will be the same. Okay? So, a matrix A is said to be normal if AH equal to AHA. Okay? So we have this definition, okay, to say a matrix is normal. Okay? So a matrix A is normal if and only if A possesses a complete orthonormal set of eigenvectors. Okay, so we know there exists a unitary matrix U and a triangular matrix T such that T equal to UHAU, right? I mean, to have this, we don't need to have any assumption for A, right? Okay, for any given matrix A, we have this already, right? We can have like a unitary matrix that upper triangulate this, right? So we have that, okay? And then, okay, let's do TTH. TTH, according to this one. Okay, TTH is going to be, you can write it. I mean, the middle part, again, cancel out each other. So we get this. Okay, and the THT will be this one. Okay, and because we know, like, A is normal, right? In other words, AH equal to AHA. So in other words, like the TTH and the THT are the same, right? Okay, if they are the same, okay, that means what? That means T is also normal, right? According to the definition of normal. TTH equal to THT, right? But remember, T is upper triangular, right? T is upper triangular. And now let's try to compare the diagonal elements of TTH and the THT because they are supposed to be the same matrix, right? They are supposed to be the same matrices. So you can try to see like this. You will find that you have the following n equations like this. Because each of them represent like the sum of some square terms, right? Okay, and the right-hand side is T11 squared. So the left-hand side has T11 squared as well, right? So the only case to make the first equation to hold is the other terms must be 0, right? Okay, and then similarly, okay, I mean you can use similar idea, okay, eventually to, I mean, find out that, okay, the Tij where I is not a j, I is different from j, to be all 0. Okay, so in other words, the U diagonalizes A, okay, because like your T is actually a diagonal matrix. The only elements that are not 0 are the diagonal ones. Okay? And the column vector of U are eigenvector of A. This is a given because like once you have like once you have the what should I say here D once you have D equal to UH AU, okay, that pretty much means like you know you apply like a U on the both left hand side. So AU equal to UD, right? And remember like if you sorry. I mean, UD is pretty much like this AU A times U 你知道我那个上个礼拜五去那个龙华科技大学去那个审查人家的学校，我发觉人家那个一个科技大学他们的那个每一个教室都有智慧白板这样子，只用手写就好了，都不需要这个鸟东西。哎，好吧 ，Anyway， 好，这些都是 orthogonal， 对不对？这些都是 orthogonal， 对不对 ？Vector， 这 x1、x2、xn。那这个地方，你等于说是这是浪打 one， 就是你那个假设那个 diagonal 是浪打 one， 浪打 n 好了。这是假设这是 d， 那你这样乘起来，这变成是浪打 one 乘上 x1， 浪打 two 乘上 x2， 点点到浪打 n 乘上 xn， 也就是说你这个 ax1 等于浪打 one x1。那 a 点，然后一直到 a 浪打 axn 等于浪打 n 乘上 axn， 所以 U is the eigenvectors of A, and the diagonal elements are the corresponding eigenvalues. Okay. So that's it for this section. Unfortunately, I mean, we can only cover up to this section. And, well, so the final will cover up to the Hermitian matrices. Okay? And any question? 任何问题？如果没有问题的话，那我们是不是就到这边下课？下礼拜记得啊，期末考下礼拜啊，不要忘了，好不好？